That must be done at your part. You have to check whether it's reflexive or not. Yes, hurry up, hurry up. Can we think about this part? Yes, my dear. So what we can do? So when you have to check whether the A divides B for A and B belongs to natural number, then for a reflexive relation, can you think about that? For a reflexive relation, R must be A comma A for all integers. It means we can say A is divisible by A. Yes or no? So it means for all natural numbers, it is reflexive. And we can elaborate it even more that you are having natural numbers 1, 2, 3, and so on. If you're having 1, 1, so you can say 1 is divisible by 1, 2, 2, 2 is again divisible by 2, 3, 3, 3 is again divisible by 3. So if all the pairs are verifying your given relation, then we can say this relation is reflexive. Clear? Okay. So here is your solution. You can go through it. Next type is symmetric relation. What is that? Symmetric relation. What actually symmetric relation means? A relation is going to be symmetric if you say that A1 comma A2, a pair that belongs to a relation, they said it must implies that A2 comma A1 also belongs to that relation. It means if I have a set, suppose A, and that is 1, 2, 3, and the relation is there R. If we're going to be symmetric, then it must look like this. 1, 2, then 2, 1 must be there. 1, 2, 3, then 3, 2 must be there, so that this relation becomes symmetric. Clear? So I guess it's clear at your part that 1, 2, its symmetric relation is 2, 1. 2, 3, 3, 2. When all the inverse pairs exist, that means inverse of that pair exists in the same relation, that relation is going to be symmetric. Clear? So in simple terms, if A comma B belongs to R, then B comma A must also belongs to R. Then the relation is going to be symmetric. Clear? So if example is there, R is there, 1, 1, 2, 2, 3, 3, and you're having 1, 2, 2, 1, and you must say 3, 2, right? So let's have a check. You have to check on your notebook that is it identity, reflexive, or symmetric. Just think about it. So my dear students, you can think 1, 1, 2, 2, 3, 3, but else pairs are also there. It means it's not symmetric, identity. If it's not identity, but all the identical pairs are there, but other are there, then no problem. Then it is reflexive. I guess it's clear. Then next, 1, 1's opposite is 1, 1. So this is exactly true pair for me to be a symmetric. 2, 2 is also there. 3, 3 is also there. Till there any confusion? But just have a look. 1, 2, 2, 1 is there. It means it's also symmetric. But 3, 2, its reflex symmetric should be 2, 3. So here 2, 3 is not there. It means this relation is not going to be symmetric. Should I repeat once again? I have taken the example that R 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 3, 2. So I've just taken from the very first type so that things get clear in our mind rather than confusion, that identity, reflexive, symmetry. So I just started from the identity. I've just checked all the identical pairs are there, but else pairs are also there. It means this is not a identity relation. So I just cross that part. Then I've just checked 1, 1, 2, 2, 3, 3 is there. But else then other pairs are there. Then reflexive says I have no problem if any other relation present there. So it means this relation is going to be reflexive. Then for symmetric, I have to check their opposite pairs also. 1, 1's opposite pair is itself 1, 1. So it is symmetric. 2, 2 symmetric. 3, 3 symmetric. 1, 2's opposite pair 2, 1. It means it's going to be symmetric pair. Then 3, 2. What I need for that? I need in the relation 2, 3, but that's not present over there. It means this relation is not going to be symmetric. I guess is it clear at your part without any confusion? Identity, reflexive, symmetric. These three types are clear in your mind. All the confusions are clear. Great. So now we're having three relations. We will spend some time over there to clear the things. Consider a set 1, 2, 3. Check if the following relations are symmetric or not. So we have to check only symmetric or not symmetric. So what I guess, can we work upon all the three relations, identity, reflexive, symmetric, so that my mind gets clear with the definition that what's going on exactly in these parts? Because it's going to be a little bit confusion for some students, and it's going to be a clear, crystal clear picture in their minds. So I want you to be crystal clear picture about that. Right, my dear friends? So let's have a look. I'm having 1, 1, 1, 2, 2, 1, 1, 3, 3, 1. We are talking about relation 1. Agreed? So just have a look. 1, 1. I've just gone through all the things. 1, 1 and 1, 2 was there. It means identity is not in their part. Right? Then, if 1, 1, because I have to just skip. In simple terms, you have to say, आपको नजर टिका के रखना है. आपको ऐसे सेट करके रखना है कि भाई मेरे को जो देखना है, मेरे को उसी पे फोकस करना है, so that मुझे मेरा आंसर मिल जाए. Getting my point clear? So you have to be focused on that part only when you're talking about that relation. So for identity, I've just looked 1, 2. Oh, it cannot be happen. It means it's not identity, right? Then 1, 2. I must search for 2, 2. That's not there. So it means it's reflexive, it's not there. Clear? Now just come to the parts symmetric. 1, 1. It's symmetric in itself. Clear? 1, 2. I search for 2, 1. 2, 1 search for 1, 2. It means they both are clear at their part. Then 1, 3 search for 3, 1. 3, 1 search for 1, 3. So it is symmetric. Is it clear? So next part 1, 1. Other pair is there, so it's not identity. 1, 1, 2 is 2, 2 is not there. 3, 3 is not there. It's not reflexive. Then let's have a look. 1, 1 is symmetric in itself. 1, 2, 2, 1. 2, 1, 1, 2. Then 1, 3 search for 3, 1, and that is not there. It means it's not going to be symmetric. Clear? Just check your answers. If already had done at your part, you can check it with me. Then 1, 1, 2, 2, 3, 3. Nothing else was there. So it's identity. If it's identity, it is reflexive too. Right? So then next, 1, 1 is symmetric in itself. 2, 2 is symmetric in itself. 3, 3 is symmetric in itself. So it means this relation is symmetric also. Here. Great. Then next type is transitive. Next type is transitive. Clear? So our relation set A is called transitive when you say A1, A2 belongs to R, A2, A3 belongs to R. Then it must implies that A1, A3 belongs to R. What mom said, it's not clear in our mind, right? So let's have a look. I want to say that if our element A, comma B, our pair is there, and that belongs to a relation R. B, comma C is there, that belongs to R. So for the relation to be transitive, see, just listen about the thing what I am saying. This is the stage 1. If first stage you have checked A, comma B is there, B, comma C is there, right? Then it must implies that you must have A, comma C for the relation to be transitive. Clear? Getting my point here? If A, comma B is there, B, comma C is there, for the relation to be transitive, A, comma C must be there. Right? But. Okay, this is stage 1 and this must be a stage 2. Right? This was a case 1. Case 2 arises. If I say A, comma B belongs to relation and there is another relation A, comma C. And you can check this part is missing. Right? Right? So if this part is missing, you can just conclude over there that this relation is already transitive because that going to be paired with A, comma B, that doesn't exist. If that doesn't exist, then it doesn't matter for you to A, comma C already there or not. Then the relation is going to be transitive. It means it must clear in your mind that if A, comma B is there, B, comma C must be there for the relation to be transitive, A, comma C. Right? If A, comma B, B, comma C are there, then A, comma C must be there to check if it is transitive or not. Right? If B, comma C is not there, then the relation remains transitive. I needn't go anywhere to check. Here, just have an example. It will be clear from an example. Let I have a relation R and I have 1, 1, 2, 2, 1, 2, 2, 3. Clear? So my dear students, I gone through 1, 1, then 1 to 2, then 1, 2 is already there. It means this relation is okay. Then next, I go to 2, 1, 2, 1, 2, 2, then 2, 2 goes to 2, 3. So 2, 3 is there. Then this is also correct. Then I must go through the another pairs. 2 to 3. 3 is not there anywhere. So this is okay. Then 1 to 2. 2 to 2. 1, 2 is there. That's also okay. It means this relation is symmetric. Do you find any pair for that you getting that B, C is there, but A, C is not there? Another example. If I must say I'm having a relation 1, 1, 1, 2, 2, 1, right? And 3, 2, 3, 2, right, say 3. And you are having 1, 3, 1. Let's say 3, 3. And then we are having 3, 1. Clear? So now we check that 1, 1 is there. 1 to 1, 1, 2 is there. That's also agree. Then 1 to 2, 2 to 1, 1, 1 is there. 2, 1, 1 to 1, 1 is there. That's all correct. Then 1, 2, 2, 3. 1, is there or not? Just look at these pairs. This one. See, 1, 2 is there. 2, 3 is there. But 1, 3 is not present in my relation. Agree or not? Yes. Can we see? 1, 2 is there. 2, 3 is there. But 1, 3 is not there. It means A, B is there. B, C is there. But A, C is not there. It means 1, 3. Just make it not symmetric. So the relation is not symmetric. I guess I'm clear at my part. And it's clear at your end. Right? What do you say? Any confusion till there? Can we go ahead? Okay. So things cannot be finished without examples. So now you're having 3 examples. Just think with me. Let's start with identity. I will not stop this thing till the end of the session. Identity, reflexive, symmetric, transitive. If these 3 things and the table part is clear at your end now, then relation is going to be a very crystal clear picture in your mind. So dear friend, let's get started. Very first, 1, 1 is there, 1, 2 is there. So identity, it's not there. 1, 1, 2, 2 is not there. Reflexive is not there. 1, 1, 1, 2. 1, 2 is the reverse. 2, 1 is there. So it's not symmetric. 3 things are clear. Let's get set for the transitive. 1, 1, 1, 2. So it must be 1, 2. It's clear. Then 1, 2, 2, 3. 1, 3 is there. Right? Another look. Then we are having 1, 3. Nothing else is there. 1, 1, 1, 3 is there. 1, 3. So the relation is going to be transitive. Yes. Okay. Then 1, 1, 2, 2, 3, 3, and other pairs are there. So it means not identity, not reflex. 1, 3 is opposite, 3, 1 is not there, 2, 3 is opposite, 3, 2 is not there, not symmetric. Then let it set for transitive. 1, 1, 1, 3. 1, 3 is there. Then 1, 3, 3, 2. Then 1, 2 is not there. What do you say? Yes or no? 1, 3, 3, 2, but 1, 2 is not there. It means the relation is not transitive, right? Then 1, 1, 2, 2, 3, 3, identity, reflexive, yes. They're reciprocal itself, so symmetric also. And 1, 1, 2, 2, 3, 3, they are transitive in itself, so they are transitive too. Is it clear at your part? So what we can say, what is reflexive, what is symmetric, what is transitive, and what is an identity relation? Is all the things are clear? Any confusion, any doubt? Okay. So we are having a question. It's an activity 2. Show that the relation R defined on a set of real numbers such that A, B, A is greater than B is transitive. Can you think about this? You have to quote the question, think about this, and just write it on your notebook. How you can think about this question. Oh, great. So I got a reply that it is transitive. Great. Thank you. So how you can think about this, that it is transitive or not when you're talking about real numbers? I can just set a pair of numbers like this only. If A is greater than B is greater than C, then it must say A is greater than C. What do you say? Right? It means if A comma B belongs to R, it says A greater than B. And B comma C, a pair exists in the relation and it says B is greater than C. And from these two relations, A is greater than B is greater than C, it must say A must be greater than C, right? So it means it says A comma C belongs to R. Right, my dear friends? Yes or no? Is it clear? Great. So what you have learned till there, you have gone through the reflexive when identical pairs are there. You have gone to the symmetric when reverse pairs are there. A comma B is there, B comma A is there. Transitive, a very important part. A comma B belongs to relation, B comma C belongs to relation, then A comma C must belongs to relation. I guess it's clear at your part, all the three types of relation, yes or no? Right, my dear friends? Clear? Then there is a minor. What you have gone through the relation till there. You have just gone through a relation is there. We have seen domain, range of a relation. We have gone through the inverse of a relation. Then we have gone through so many types of a relation, that is void relation, empty. When R is does belongs to empty, there nothing is there. When R belongs to full Cartesian product, what is identity relation? When you are having A comma A, nothing else is there. Reflexive says other can be present. Symmetric says A comma B comma A. And what transitive says, if A comma B belongs to relation, B comma C belongs to, it must say A comma C belongs to relation. So is it clear? Any doubt till there? Yeah. Next part, we are having equivalence relation and equivalence classes. What is that? One thing is you already done. Three types: reflexive, symmetric, transitive. These three types of relation are clear. If a relation contains all the properties of these, a reflection is reflexive, symmetric, as well as transitive. When all the three relation is there in one relation, that relation is going to be equivalence relation. Clear? Noted. It means a funny example is there. We can say a perfect suit match suits when you have just make a fixed structure in your mind that it must be a graduate, it must have a good government job and some height, we can say that much height. So it's also a fixed curriculum. That means equivalence relation is only when it contains three properties, three qualities. It must be reflexive, it must be symmetric, and it must be transitive. Is it clear to you? When all the three types of relation exist in one relation only, that relation is called equivalence. Clear? And what is reflexive, symmetric, transitive? That is clear already in our mind. What do you say? Great. So now we are having example that a relation R in the set Z. Z means integer of all integer defined as R, X comma Y. X minus Y is an integer, determine whether the equivalence or not. So what you have to check actually in these types of question, you have to check reflexive, right? You have to check symmetric. Then you have to check transitive too. If all three agrees, then this is equivalence. Can it be done at your part? See, for reflexive, what you will get? If x comma x is there, right? Then you must say x minus x is 0. And 0 is integer. No doubt in that. So it means it is reflexive. Then about symmetric. If I say x comma y is there. So x minus y is some integer, let's say lambda. Then y comma x must be there. So y minus x give you minus lambda, and they both are integers. It means it's symmetric to transitive. If you say a comma b belongs to a relation, that means a minus b will give you m, right? And m is integer. Then b comma c is a pair or a Cartesian pair that is present in your relation, and you say b minus c is also a relation. What I will do? I will simply add these two things. It means a minus b plus b minus c is equals to m plus n. B is b cancel. So a minus c will give you m plus n. Let me ask, if an integer is added to integer, you will get an integer. It means this is also an integer. So a comma, it implies a comma c belongs to relation. So it means my relation is transitive too. So if a relation is reflexive, if relation is symmetric as well as transitive, then the relation is equivalent. So any confusion is there till there? Okay. So this is the what we have done. We have gone through these three things. We have just proved it reflexive, we have proved it symmetric, and we have also proved that transitive. If the relation contains these all the three properties, then it is going to be an equivalence relation. Everything is settled in our minds right now. Okay. Then next thing, you have to show that the relation f defined on a set real numbers a comma b belongs to f if and only if a modulus is equals to b modulus is an equivalence relation. And what I think, you just note it down and just try after the session. What do you say? Just note it down. It's an activity for you. Just note it down and do at your part. Okay. Then we are having one last topic for the session, that is equivalence classes. What is that? R is be an equivalence relation on a set. Then set of all elements related to an element A of A is called equivalence class, right? When you're saying that R be equivalence relation on set A, then set of all the elements to an element, we will select one element, let's say A. If all the elements are related to that element, that is going to be an equivalence class of A. And it is denoted by this square brackets to A. So it means A square bracket means X belongs to A comma X belongs to relation. Let's have a look how you can think about this. You're having an example that equivalence relation R. You already know that this relation is equivalence, right? Then what are the equivalence classes? It means you are having a set 1, 2, 3, 4, 5. What we can do? A relation is defined to you 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 3, 3, 1. Just have a look for your understanding only. This relation is reflexive? Yes. Is this relation is symmetric? Yes. And you can check this relation is transitive too, because other pairs doesn't affect only the 1, 1, 1, 3. And rest 3, 3, 3, 1. That's okay. 1, 2, 3, 3, 2, 1, 1, 1. 3, 2, 1, 1, 2, 3, 3, 3. So this is transitive. Clear? So the relation is equivalent just for your satisfaction only. You can have a look. The relation is reflexive or not. Symmetry, equivalence or not. Right there? So what we can do next? We have to check the equivalence classes. How you can do. Just have a look. Example is there, relation is there, set is there. If I'm checking about the element 1, what I can do? X belongs to A. Remember, we have in the definition written X belongs to A comma X belongs to relation. Then this is equals to A equivalence class. So equivalence for class 1, it means X belongs to A, 1 comma X, then it will be 1 comma 3 only. For the 2 comma X, it's 2 only. For 3, it's 3 and 1 only. For 4, it's 4 only. Just check. I guess you're getting confused. See, for 1 means when one pair is there, what are related to X? What can be at X place when very first element of your pair is 1? See, it can be 1, it can be 3. So you have a set 1 comma 3. For 2 only, you are having one element, that is 2. For 3, you are having 3 comma 1, 2 possibilities. 4, 1 possibility, 5, 1 possibility. Is equivalence class is clear at your part? Any confusion till then? So you are having one activity. You have to write the equivalence classes for this. Just write it with me so that concept is clear at your part. For 1, what you can say? It must contain 1 and 2. It means for equivalence class for 1 is 1 comma 2. Then 2, what you will see? It's 2 and 1. So it will contain 2 comma 1. For 3, it contains only one element, that is 3. Clear? So this will be the activity. This will be the thing that you have to done. I guess equivalence classes as well as equivalence relation and along with reflexive, symmetric, transitive. All the things are clear at your part. Any confusion till there? In simple language, we are already about to finish with the relations. Great. So you have to check. Let's have a look. A set is there. 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2, 2 comma 1. You are having one relation, another relation, right? You have to check whether these relations are reflexive, equivalence or not. What you can do? Firstly, they said union. A union is very clear to us. Remember how we can do the union? Only class 11, we have already gone through the union. What was that? You have seen that it can be, you will write all the pairs of first set. That means 1 comma 1, 2 comma 2, 3 comma 3, then 1 comma 2, 2 comma 1, then we will come to 2 comma 3, 3 comma 2. You have to check either. I will do the first part for you. You have to check reflexive, symmetric, transitive, right? So what we can do? Reflexive, 1 comma 1, 2 comma, yes, it's reflexive. Symmetric. All the opposite pairs are there. It's symmetric. For transitive, 1, 1, 2, 2, 3, 3. There no problem. 1, 1, 1 to 2, 1, 2. 2, 1, 2 to 2, 2 to 1. 3, 1 to 2, 2 to 1, 1, 1. It's great. They are reflex. Then 2 to 1, 1 to 2, they are yes. Then 2 to 2, 3, 2, 3 is there. 3 to 3, 3, it's there. 3 to 2, 3, 3. Everything is there. So the relation is going to be transitive also. Yes or no? Rest two parts you can do it. Okay. Now, from the activity we derive some results. What was that? If two relations are there and they are equivalents in itself, that means R1 is equivalence, R2 is equivalence, then their union is equivalence, their intersection is equivalence. In fact, their inverse is also equivalence. You can note these points at your part, that if two relations are already equivalents in itself, it means their union, their intersection, in fact, inverse of a relation is also going to be equivalence. Noted? So the number of relation on set A with n element, if a set is having n elements, then number is 1. If 2, then number is 2. When number of elements are 5, then it's 5. When number of elements is 3. It's 15 when number of elements is 4. Clear? Clear? Any doubt, any confusion? Great. So this was all about today's session, and we're about to already finished about relations. I hope this is clear at your part without any confusion. Just go through all the things, once go through all the notes, and must have a look on your NCERT also. So see you all in the next session with the next part, that is function.